Hi everyone! For today's video, we will investigate how surjective functions are used in graph theory and network routing, and investigate how injective and bijective functions are used in advanced topics like graph theory and cryptography. In our first line of our code, we will explain how surjective functions are used in graph theory and network routing. A surjective function ensures that every element in the target set has at least one corresponding element in the domain set. This is crucial in network routing to ensure resource allocation and load balancing. In this code, the function allocate task takes two parameters, nodes and task. An empty dictionary named allocation is created. Each key in this dictionary is a node from the nodes list, and the corresponding value is an empty list. This dictionary will be used to store the task allocated to each node. The function iterates over the task list using a for loop, which provide both the index and the task. For each task, a node is selected based on the index using the modulo operator, i%len nodes. This operator ensures that the tasks are distributed evenly across the nodes in a round-robin manner. The selected task is appended to the list of tasks for the corresponding node in the allocation dictionary. Finally, the function returns the allocation dictionary, which now contains the tasks distributed among the nodes. Second, we will explain how injective and bijective functions are used in advanced topics like graph theory and cryptography. First, we'll explain the graph theory. This code is about graph isomorphism. The function is isomorphic takes two parameters, graph 1 and graph 2, which is dictionaries representing the adjacency list of two graphs. The function first checks if the lengths of graph 1 and graph 2 are different. If they are, the function immediately returns false as graphs with different numbers of nodes cannot be isomorphic. An empty dictionary named mapping is created to store the correspondence between nodes in graph 1 and nodes in graph 2. The function iterates through each nodes in graph 1 using a for loop. For each node is graph 1, it iterates through each node in graph 2 using a nested for loop. Within the nested loop, the function checks if node 2 is already in the mapping dictionary. If node 2 is not in the dictionary, the function proceeds to the next check. The function compares the number of neighbors of node 1 in graph 1 with the numbers of neighbors of node 2 in graph 2. If they have the same number of neighbors, the function maps node 1 to node 2 in the mapping dictionary and breaks out of the inner loop. After completing the loops, the function checks if the length of the mapping dictionary is equal to the length of graph 1. If they are equal, it means all nodes in graph 1 have been successfully mapped to unique nodes in graph 2, and the function returns true, otherwise it returns false. This code is also of graph theory. It's called perfect matching in bipartite graph. This code is a bijective function. In a perfect matching of bipartite graph, each node is one set is matched with exactly one node in the other set. This forms a bijective function between the two sets of nodes. The input bipartite graph is a list of tuples representing the edges in the graph. The function creates an indirect graph G and adds the edges from the input graph. And then find the perfect matching using nx max weight matching and returns the matching edges. The output shows that each node in the first set A1, A2, A3 is perfectly matched with a unique nodes in the second set B1, B2, B3. And last is about cryptography. This code, called symmetric key cryptography. The function encrypt and decrypt takes two parameters, message and key. An AES cipher object is created in CBC mode using the provided key. CBC mode requires an initialization vector to ensure that identical plaintext blocks are encrypted differently. The plaintext message is padded to ensure its length is a multiple of the AES block size. The padded message is then encrypted using the AES cipher, producing the ciphertext. The 4 used during encryption is retrieved from the cipher object and stored in the variable. The 4 is necessary for the description process to ensure proper description. The ciphertext bytes are stored in the variable CT. A new AES cipher object is created in CBC mode using the same key and the provided use IV. The form must be the same for both encryption and description to ensure the process is reversible. The ciphertext is decrypted using the AES cipher, resulting in the padded plaintext bytes. The decrypted bytes are then unpadded to remove the padding added during inscription, restoring the original plaintext. The function returns a tuple containing the ciphertext bytes and the descripted plain text string. And here's our output.